Today, we're diving into the secret world of debugging. It's really the detective work that teaches computers how to learn from their own mistakes, which in turn makes all of our technology way smarter and more reliable. We're going to follow a single, simple piece of code on its journey from, well, broken to brilliant. So let's get right into it.
You know exactly what I'm talking about, right? You measure everything perfectly, you follow every single step, and the cake still comes out flat. Well, computers have that exact same problem. They follow their recipes to the letter, but if there's a tiny flaw in the instructions themselves, the end result is going to be a total mess.
And in the world of computing, that recipe is called an algorithm. So for this explainer, we're going to track one specific algorithm. Its job sounds super simple. Just find the largest and smallest numbers in a list. But as you're about to see, even the most basic instructions can hide a really critical flaw.
Okay, so let's check out the first attempt. On the surface, the plan seems totally logical. I mean, what could possibly go wrong? To find out, we need to pull out the right tool for the job.
And our main tool for this investigation is something called a trace table. You can think of it like a slow-mo replay that lets us watch the computer think step by step. It's how we're going to find exactly where the logic starts to break down.
So let's follow the logic here. The computer gets fed that list of numbers you see up top. Now, look at the first row of the table. The computer sees the number 400 and sets it as the largest value. Okay, makes sense. Next row, it sees 800, and yep, it correctly updates the largest value to 800. But look at what's happening with the smallest value. It's just never updated. The algorithm goes through the whole list, but the output for the smallest number stays blank. Let's see what that really means.
And there it is. That's the smoking gun. The algorithm did its job, kind of. It correctly found 900 as the largest number, but it completely missed 110, which was the smallest. So our first attempt is officially a failure. Time to go back to the drawing board.
All right, on to attempt 2. The programmer thinks they know it went wrong, and they create what the source material calls a better algorithm. The intention here is good, but as we're about to find out, sometimes fixing one problem just ends up creating a totally new one.
Let's look at the thinking here. The fix is to set the smallest number to some ridiculously high value, in this case 1 million, and the largest number to 0. The idea is, hey, any number in our list is definitely going to be smaller than 1 million and bigger than 0, right? It seems like it guarantees that the first number we check will instantly become our new smallest and largest. It's a clever idea, but it's based on one massive assumption.
And this is the fatal flaw. What happens if the list of numbers we give it is full of negatives? The algorithm would never find a number smaller than its starting point of 1 million, but it would incorrectly say that 0 is the largest number. Or what if all the numbers are over 1 million? It might find the correct smallest number, but it would fail to find the largest. This better algorithm is actually way more fragile because it just assumes it knows what the data is going to look like.
So, all of this brings us to attempt number 3. After learning from both of the earlier failures, the designer finally came up with an algorithm that isn't just better, it's actually robust. It's smart. And right here, you can see that evolution in action. On the left, you've got that fragile assumption-based algorithm, and on the right, the final robust version. Now look closely at the very first step right after start. The old version just sets these random arbitrary numbers. The new one does something so much smarter. Let's break down exactly what changed.
Here are the 2 critical fixes that made all the difference. First, that smarter start. Instead of guessing a range of numbers, the algorithm just takes the very first number from the list and immediately sets it as both the largest and the smallest value to start with. It makes 0 assumptions. It uses the data itself to get going. And second, the corrected counter. Since it already used that first number, it only needs to loop 9 more times to check the rest of the list. This isn't just a patch, it's an elegant solution that was only possible because of the previous failures.
So, why did we just spend all this time looking at one little algorithm? Because this whole journey, from a flawed idea to a bad fix to an elegant solution, that is the very heart of all innovation and problem solving. And it goes way beyond just writing code.
So, the moral of our little story is pretty clear. Errors aren't just mistakes to be erased, they're actually opportunities. The process of finding them forces us to think logically and to really confront our own hidden assumptions, the things we thought were true. Each failure, when you really analyze it, leads directly to a stronger, more reliable solution in the end. This cycle of testing, failing, and improving is what makes all the tech we rely on actually work.
And that leaves us with one last big thought. From our banking apps to our social media feeds, we are surrounded by incredibly complex algorithms making decisions for us. This whole explainer was about finding one single bug in a really simple system. So, what hidden assumptions, what tiny logical flaws might be hiding in the vastly more complex systems that we trust without a second thought every single day?